All right, so let's get started on the section 2. So today we are going to have a review of the CMOS scaling, and then if we have time, we will talk about the industry trend. So first of all, I'd like to have a quick review of the MOSFET, and I assume that all of you have basic understandings how a transistor is working. And then we'll talk about the CMOS scaling trend, and then finally the industry landscape. So this is the structure of a planar MOSFET, and this is the gate, and then this source and the drain. So this is like a cartoon figure from the bird eye view. But if you are a circuit designer, then you will deal with the layout on the right. So then you, as a physical designer, then you will specify the design rule. Of course, follow the guidelines from the PDK, process design kit. Then you will design those like gate lengths and the width, and also the contact size and the spacing between contact to the gate and also to the diffusion region and so on. So this is the MOSFET layout for the planar MOSFET. This is used in the older technology node. And then here we are in this silicon CMOS industry. So the industry is built on top of this CMOS technology. And we have NMOS and PMOS. And NMOS, when you have the positive gate voltage, then you are going to turn on the channel. So channel will be inverted from the P type to the N type. That means electrons will be induced to form the channel. And then with the VDS, the drain voltage applied, then you have current flow from the drain to the source, which means the electrons are flowing from the source to the drain. So then PMOS, everything is reversed. All the voltage polarities are reversed. So then you will have a negative voltage to turn on the PMOS. And then the source and the drain definition will also be reverted. And then NMOS and PMOS can be fabricated on the same substrate. And so normally you will start with a P-type substrate. And then this is for NMOS region. So for the PMOS, you need to first design a N-well to basically dope this region to be N-type, and then use this as a PMOS substrate. So I believe those are the basics, so I will not spend too much time here. So here I'd like to talk about the MOSFET operation principle using this 3D band diagram. So the band diagram is very important to understand how the device works, how the transistor works in this case. So here, if we look at the transistor, this is like we tilt the transistor by 90 degrees. So here you are looking at, if you are looking at, let's say from this perspective, you will see the top view of the transistor. So this is the source, this is the drain, and this is the gate. So here in this case, this will be your L, and this will be your width, W. So here in this direction is in the silicon substrate. So here the band diagram in the 3D view, because this is NMOS transistor, so you have P-type substrate, and you have the band diagram like this. So here, the first is EC, conduction band, and then EV, valence band. And the pin junction will have this built-in barrier between the source and the channel to the drain. So you have this kind of barrier from the source to the drain. So basically electrons are stored in the source or the drain. So in the channel you don't have electrons when the transistor is off. So this is initial state. So those balls are electrons. You can think source and drain are full of electrons, but there's no electrons in the channel when the Vg equals to Vd equals to 0. And then what will happen is that when you apply gate voltage, so the gate voltage larger than 0, in the energy band diagram, there is a principle. The positive voltage will bend down the band because the band is related to the electron's energy, and the electron is negatively charged. The positive voltage will push down the energy of electrons. So in this case, because the gate voltage is applied, so the band will be bent towards the surface of the channel. The surface means the interface between the silicon and the silicon dioxide, the gate dielectric. So the band will be bent. As a result, this barrier between source and channel will be reduced here. You see this barrier height is reduced compared to the original state. So that means the electrons will have the probabilities to jump over that barrier. So initially, you have the large barrier, let's say source to the drain, like this. When you apply gate voltage is tied to the channel region, right? Then this barrier will be reduced. This barrier will be reduced. So electrons can move over the barrier. Especially now if you apply the drain voltage larger than 0. So if you apply drain voltage here, this is due to the Vg larger than threshold, let's say. So if the drain voltage is also larger than 0, so the drain side will be bent down. So the electrons will fall along this slope of the band diagram. So electrons will flow like this. This is how you introduce the current in the MOSFET. So if I teach the undergrad like device physics, semiconductor device physics course, I will always use this analogy that electrons are like water. Then water will go to the lower potential. So once you have this kind of energy band diagram, then naturally the electrons will fall down along this slope. So if you think about the PMOS, everything will be reversed. PMOS, if you use an energy, then holes are like bubbles in the water. Holes will always go to higher potential. But we will not talk about the PMOS here. So here for electrons, once you turn on the transistor, then it will be flowing. So any questions here? All right, then let's review the IV characteristics of the transistor. I assume that you are familiar with this. So first is this output characteristic, that is between the drain current versus the drain voltage. So you have this kind of curves, because each curve corresponding to different VGS. So as you increase the VGS, then you are going to have higher drain current. So the other one is called the transfer characteristic. This is ID versus VGS. And then you can have different curves as well. So you can have two VDS, for example. So higher VDS will induce larger current. But most of them will merge to this point. This is like the threshold voltage. So below that, the current is very minimal. And above that, you have a kind of very large current respect to the Vg. So this is a typical transistor characteristics. So basically, the drain current is controlled by either the gate voltage or the drain voltage. And here are some definitions in the output characteristics. For example, here, this part is this child region or the linear region, right? Child or the linear region. So in this region, the VDS is small. So the transistor can be approximated as a resistor. Why is that? Because here you see this ID is proportional to the VD. So it's a linear resistor in this case, in this region. So here this resistance is called the channel's on resistance. And then this is given by the 1 over the slope here. This is in the linear region. And then once the transistor reaches this, let's say this is like the boundary. So then this is the saturation region. The current will no longer increase significantly, of course, due to the short channel effect or channel length modulation effect. Then the transistor current will slightly increase. And then the slope, the differential slope here is called output resistance. So this is like a small signal concept. This is for analog circuit. Then you are thinking that you have a DC bias here, and then you have small signal disturbing the transistor. Then you will have the output resistance, the small RD. So this is for the analog circuit design. This is output resistance of the transistor. And then you can also define the transconductance, which is the delta ID versus delta VGS. So this is also a small signal concept. So if you have any change in the VGS, then how much change you get from the drain current at certain bias. So this is called the transconductance. But I would say in this course, we are not going to deal with the small signal model. So mostly we will use the large signal models, like what is the channel on-state resistance and what is the maximum and minimal current. So those are the large signal concepts. We are not going to deal with the small signal concepts. All right, so here I want to spend a few words on the subthreshold current. So this is important for many discussions in this course. And sometimes in the undergrad courses, this part will be skipped. But I hope that you can still have some knowledge about the subthreshold. So basically here what we show is ID versus VG. But the ID is in the log scale. So this is important to show the subthreshold. So in the log scale, then the small numbers will be amplified. So that's why you see the current even below the threshold voltage here. And typically it will be a straight line in the subthreshold. And here we can define two parameters. One is I-on. This is on-state current of the transistor. And I-on is when the gate voltage is a power supply VDD, and then the drain voltage is also power supply VDD. So this is the maximum current you can get from the transistor, and it's here. And then there is off current. Off current is not zero, okay? The off current definition, gate voltage 0. So here you see the gate voltage is 0, but you have the VD equals to VDD. So of course, if VD is 0, then no current flow, then the current is 0. But this is not the way we define the I off. We define the I off in this condition. This is because in many circuits, you will have this kind of configuration. Right? So that means here the input is 0, but if your power supply is still on, you will have the I off in this case. Of course, this I-off can be very small because this is in the log scale, but it's not negligible. And this is the reason for your leakage standby power of your system. For example, your phone, right, you are not running any app in the sleep mode, but your battery is still being drained. Why is that? Because you have to maintain those logic transistors, especially the SRAM, are still in this standby mode, and then you still have the current flowing from the VDD to the ground in the standby mode, even if the input is 0. But once you have the power supply on, then you have the leakage current, this I-off, and this is burning your power in the standby mode. Okay, and then the subthreshold slope S is defined as 1 over the slope in this curve. So it's defined as this slope, which is the derivative of the log ID over Vg, and then 1 over that. So you have the power reactive 1 here. So in other words, you can think this is the slope here. The S is defined when you reduce the current by 1 decade. That means 10 times. How much voltage you need to reduce. And the theoretical minimum will be 60 millivolts per decade for MOSFET, no matter which foundry is fabricating the MOSFET. This is due to the physics. So that means to reduce the current by 1 decade, you need to reduce your gate voltage by at least 60 millivolts. So how does this 60 millivolt come from? So here we have some equations. I don't require the deep understanding. This is really deep into the device physics. But here let's have a quick discussion. So here for this definition, you can use the chain rule and then split that into the derivative of the gate voltage over this phi s is the surface potential. That is the potential of the panel's surface. And then the second one is the derivative of the surface potential over the log ID. So the first term essentially tells you how effective your gate voltage you applied externally can affect the channel potential internally. So this is essentially the coupling from the gate voltage to the channel. So that means what? So here if you think about the transistor, you apply the gate voltage externally, but the channel has certain voltage potential. So then the first term is how effective that the external gate voltage control the channel surface potential. And then the second term is this phi s over log ID. This tells you how sensitive the channel potential change can affect the current flow, of course here in the log domain. And this is essentially due to the barrier concept we have earlier. So you think that we have this barrier, source to this is the source and channel and drain. So this is the channel like surface potential. And this barrier height. And essentially the second term tells you if you change this phi s, this barrier a little bit, then how much current you can flow over. So this is how the second term. So the first term you can express that into this capacitor model, because essentially here you can think this is like two capacitors between the gate oxide, and then in the channel you have the depletion cap. So essentially it's like Vg respect to the the phi s respect to the Vg, and then from the capacitor divider, then you can have this equation. So essentially it's this COX plus CDM over COX, because this is a divider, voltage divider in the capacitor format. And then the second term here, this one is due to the physics. This is due to the Boltzmann distribution of the carriers, the electrons, in the source region. So the electrons, so basically we'll have like a Boltzmann distribution. So most of the electrons will stay in the valley here. Then exponentially less electrons will have the higher energy to jump over. So to describe this statistics, then you have to use the Boltzmann constant K times the temperature T, because higher temperature will excite more electrons to jump over. So essentially KT over Q is the thermal voltage. And thermal voltage, if those are the physical constants. So if you do that, this will be at room temperature, will be like 26 millivolts at room temperature. And then here, this natural log 10 is when you convert the natural log E from the natural log 10, because here in our plot we use log 10. But in the equation, typically you have this kind of exponential like KT over Q. If you convert this to log, this is based on the natural log E. But if you convert to the natural log 10, then you get this coefficient, and this is 2.3. So 26 millivolts times 2.3, you will get 60 millivolts. This is how you get the 6 millivolts. And then the first term will be always equal or larger than 1, because it's 1 plus something. So that's why here we derive eventually S is always equal or larger than the 60 millivolts per decade. So any questions here? I know it's a little bit complicated. And here this S is important. Why is that? Let's give an example. So if you want the transistor to be off, really off, then typically you want the on-off ratio here more than like 10 to the power 5. So if you like on current is about like 10 microamp, then you want the off current is like 100 nanoamp or below. So you need to have on-off ratio. And then if you want the on-off ratio here, let's say from this current at the threshold over the I off, larger than 10 to the power 5. So that means you can, if this ratio is large, that means I off is pretty small. You can ignore that. This is what you wish. So if you want to have this on-off ratio, let's say from the threshold current to the off current larger than 10 to the power 5, that means here the Vt needs to be larger than what number? Anyone? I have a quick calculation. So what is your minimal threshold voltage? If you want to have the current larger than 5 orders. 5 order means 5 decades. Each decade you need to pay for 60 millivolts. 5 decades you need to have 300 millivolts. So that's why today's transistor is really hard to scale down the threshold voltage. You cannot reduce the threshold voltage because you have to maintain this on-off ratio. This is caused by the physics. You cannot do anything because here those are the physical constant, 60 millivolts. So any questions here? All right, so then let's talk about the short channel effect. So that's why it's very hard to design the transistor in today's nanoscale because of the short channel effect. So here, this is a band diagram from the source to the drain. And in the long channel, you can have the well-defined barrier. So then you can have this ID versus VG in the log scale. So this is your good transistor, non-channel transistor characteristic. And you can maintain the on-off ratio, for example, here, larger than 10 to the power 5. But as you scale down the channel length, so then you see that if you become short channel in the red one, so because the source and the drain now is so close, this source and the drain is so close, so this barrier height will be affected by the length of the channel. So this barrier basically controls the leakage current. So the electrons are stored here. Now if the drain is so close, so the electrons are easier to jump over, then that means you will have the large off current. And also the VDS will affect the short channel will affect the drain current. So here you see that in the long channel, as you change the VDS, then you will push down the drain side voltage and energy potential. But then the barrier to the source will not be affected because they are far away. But in the short channel, if you change the drain voltage, it will be easily affect this barrier height. That means the current will be very sensitive to the drain voltage. That's why the saturation region, the current no longer saturates because the drain voltage can easily change the current in the short channel transistor. So those are the challenges introduced by the short channel effect in the transistor design. Or let's put it another way. So the transistor, if you think fundamentally, should be a gate-controlled device. You only wish that the gate voltage can turn on or off the transistor. You don't want the drain voltage to influence the transistors on and off. But in the short channel case, the drain is so close to the source. So the drain voltage will also affect the channels on and off. And then it's becoming more and more difficult to turn off the channel because the drain voltage is so close to the source. So those are the considerations we need to basically optimize the transistor structure to compensate some of those non-ideal effects. Okay, so here, why do we care about the I-on and I-off? We define the I-on and I-off of the transistor, right? So why do we care about that? So here we plot the on and off current. This is for NMOS and this is for PMOS. And this is from Intel's data. Intel 45 nanometer versus 32 nanometer. So here you see that as we scale down the transistor, then we can either improve the on current or we can reduce the off current. So for example here, we can, if we fix the on current to be 1.4, then scaling can help you to reduce the off current by 5 times. Or if we fix the off current to be 100 nanoamp per micrometer, then it can improve the on current by 14%. So why do we care about that? Because in simple digital circuit formula here, you see that the circuit delay is given by the capacitance that the circuit needs to drive, multiplied by the power supply VDD, divided by the on current. So if you have larger on current, you can charge and discharge those capacitor load faster. So the circuit can be operated faster, delay will be reduced. And also from the power point of view, the leakage power is given by this off current times VDD. So we also want to reduce the off current. So that's why we care about the on and off. So here, in one technology node, actually the foundry will offer you different options for the transistor. So that's why we have a curve here. So for example, in the 32 nanometer node, the foundry will offer you technology in this point, or this point. So it will have a trade-off between the on and off current. So larger I on also means larger I off, but probably exponentially larger I off, because here you see the relationship. You change I on by a little bit, from 1.2 to 1.6, you change by like 20-30%. Then the off current will change by 10 times, like 10 to 100. This is because off current is in that log scale. Any change will be amplified in the log scale. But the industry, the foundry, will still offer you different options, because for different circuit, you may need different transistors. And typically, they will call this, for example, the high performance transistor, and the high performance transistor, low power, and ultra low power. So you have a selection of those transistors to choose in the PDK. This is typically you will see. Any questions? All right, so then next, let's talk about CMOS scaling. So let's first look at this chart. This summarizes the technology load, and then the relationship with the gate length of the logic transistor. So tech node, this is typically used in the industry. Let's say from 1992, it's about like 500 nanometer node was introduced, and then 350, 250, 180, 130, 90, 65, and beyond 65, then there are some variations in the tech node, because different companies now choose their own definition. So like Intel Core 45, TSMC Core 40, Intel Core 32, TSMC or GlobalFoundries Core 28, and so on. So the tech node, of course, is the keep scaling, but we will say that the tech node doesn't mean anything. So this is what I want to emphasize. So the tech node does not correlate to any physical dimensions on the chip. It's purely a symbol for the company these days. Or you can think it's an advertising name for the company. It's a symbol. So here, the gate length in the red one, you will see that maybe in the very early days, those two are correlated. But after that, the gate length has a very aggressive scaling. But in the past 10 years, the gate length scaling basically stopped. So this is due to the short channel effect, as we discussed earlier. It's impossible to make the source and the drain so close. And from the physics point of view, the electrons wavelength, electrons is from the quantum mechanics, but due to the duality, it's a particle and also it's a wave. So electrons wavelength is 13 nanometer. So that means it's possible to find the electrons anywhere within that 13 nanometer range. So it's impossible to make the transistor source and drain close enough. So that's why here today's transistor, even for most advanced 7 nanometer, 5 nanometer process, the physical gate length is about 20 nanometer. So you have to separate the source and drain. So here you see that's why the gate length almost stopped scaling. The tech node keeps scaling. That means nothing, okay? The tech node is just a symbol. And here we highlight some of the key innovations introduced in certain technology nodes. For 130 nanometer node, industry switched from the aluminum interconnect metal wires to copper, because copper has lower resistivity. And in 90 nanometer, the stream silicon is introduced to the channel to improve the mobility. And 45 nanometer high-K metal gate was introduced to improve the gate electrostatic. And then 22 nanometer FinFET was introduced. We will talk about those in more details later. But here, the most important thing, tech node is a symbol, does not correlate with any gate length. And the gate length scaling almost stopped these days. Then you may wonder, okay, if the gate length no longer scale, then what drives the Moore's law? What is scaling, right? So here, this is what is really scaling is this contact gate pitch and metal one pitch. So this one is continuous scaling. So here we plot the contact gate pitch and metal one pitch. So what is that? So from the layout point of view, so this is the contact poly pitch. So you can think that is a transistor. Let's say you have a transistor, right? And then you have source and drain contact. Or let's draw a transistor. And then you have the contact. So this gate length does not scale. Okay, this LG. What is scaling? Is the center of the contact to the center of the contact. This is called the contact gate pitch, CGP, or sometimes it's called CPP, contact poly pitch, because historically the gate is made by polysilicon, so it's also called CPP or CGP. So this is scaling, okay? So that means you have to shrink the spacer, the thickness, the length or the distance between the contact to the gate, and also the contact diameter. So those dimensions are scaled these days instead of the gate length. Gate length no longer scale. And also this is along the channel direction, and then and perpendicular to the channel direction from the top view layout, you have the metal one pitch, because metal one will. So basically the contact poly pitch defines the X direction, and in the Y direction you have the first metal one's pitch. So those are getting close. So here we show the contact gate pitch and metal one pitch, and it follows this scaling, even to today's 10 or 7 nanometer. Of course, you see some slow down of the scaling, but it's still moving along this direction. So here in 5 nanometer, here I have those numbers that give you the G means the contact gate pitch. That 48 means 48 nanometer. M is metal. Metal is 30 nanometer. So L1 means only one layer of the transistor. So those are the key metrics to evaluate the transistor density these days. Has nothing to do with the gate length. The contact gate pitch and the metal one pitch. And of course, those future loads, this is a projection. It's not manufactured yet. But as you see here, beyond the 1 nanometer, we don't know what's the solution. Basically, the contact gate pitch will run out of space, because this one cannot scale, and you shrink those contacts, but still you need some space for that. So you will run out of the space, probably end of this decade, 28 or 30. So at that moment, you have to do the 3D integration. So you have to have L2, L4, like 2 layers of transistor or 4 layers of transistor to keep increasing the density of the logic. Yes. Of course, this is the projection. We don't know, right? But this is on the roadmap. So here, this is more definition about the contact gate pitch. So isolated transistor, those are two separate transistors from the layout point of view. This is not the contact gate pitch transistor. So the contact gate pitch transistor is something like this, okay? So the transistor will share the source or drain, and you will have one contact between, like, let's say, two gates. And then from the center of the contact to the center of the contact, this is your CGP. So why is this important? Because from the layout point of view, you will see those transistors. So this is a simple two-input NAND gate. And you know this is the NMOS, this is the PMOS. And you see in the PMOS region, those are the contact gate pitch transistor. Those two gates share one contact. And if you look at the layout of the digital circuit below 65 nanometer, most of the transistor will be this kind of contact gate pitch transistor. All right, so then if you use the CPP and or CGP and M1 pitch to define the logic transistor cell area, this is what you will have. So in the 16 nanometer node, by TSMC's definition, the CPP or CGP is 90 nanometer and M1 pitch is 64. So let's say the CPP 90 and this is 64. And then different companies will have their own definition, okay? So that's why here the tech node, like 40 nanometer, 10 nanometer, means nothing. And Intel's 10 nanometer is getting close with TSMC's 7 nanometer. That's why Intel folks say that TSMC is cheating in the tech node naming. Anyway, I don't want to get into that business. So, but this is from the layout point of view, this really determines the density of the transistor. All right, so I think the time is up, so we'll stop here. Let me see if there are any final questions from the chat. Any questions here? Yes? Sorry, I couldn't hear you clearly.
So when we are like load planning a process, and you have its own local charge, right?
Yes.
And so when as we go L1, is there any consideration that needs to add those closer to the L2 level of the charge?
Okay, you are asking about the physical design, like where to place those L1 and L2. I think different companies will have their own choices. So there's no like unified design rule to say that this must be close to the L2 cache, must be close to the ALU. So this all depends on the overall design. And yeah, so you can manually change the locations, and then you run the synthesizer, you will see the performance of those impacts. I think those companies must have optimized for their workloads and target applications. There's no unified design. All right. So.